Imagine standing at the edge of the known universe, where invisible bullets of pure energy streak through the cosmos at nearly the speed of light particles so powerful they've traveled billions of years across galaxies, carrying secrets from the most violent events in existence. These aren't science fiction, they're cosmic rays, the universe's most energetic messengers, and they're crashing into Earth's atmosphere right now, unseen but unstoppable. Every second, thousands of these subatomic projectiles pierce through you, through everything, carrying more energy than the world's most powerful particle accelerators. Where do they come from? What cosmic cataclysms launch them into the void? And how do they defy everything we thought we knew about physics? For over a century, these particles have baffled scientists, leaving trails of questions in their wake. Some originate from exploding stars, others from supermassive black holes feasting on galaxies' forces so immense they warp the fabric of space-time itself. But the real mystery, some cosmic rays pack so much energy they shouldn't exist. Dubbed, "Oh my God" particles, a single one can carry the kinetic energy of a baseball pitched at 60 miles per hour, all condensed into a speck smaller than an atom. How does nature accelerate particles to such impossible speeds? The answers might rewrite our understanding of reality, revealing hidden engines of destruction and creation lurking in the cosmic dark. This is a journey to the edge of physics itself, where the ordinary rules break down and the universe reveals its most extreme face. Over the next 30 revelations, we'll trace these particles back to their apocalyptic origins, from colliding neutron stars to the hearts of distant quasars. You'll discover how scientists turned mountaintops into particle detectors, why Antarctica's ice hides clues to extraterrestrial thunderstorms, and how a single cosmic ray might hold the key to mysteries older than our solar system. Buckle up, we're diving into the invisible storm that rains down on us all, uncovering truths that will make you see the night sky not as a quiet expanse, but as a battlefield of unimaginable forces. The universe is far stranger, far wilder than we ever dreamed. Let's explore it together. Here's something that might surprise you: cosmic rays aren't rays at all. The name is a cosmic misnomer, a leftover from a time when scientists weren't quite sure what they were dealing with. Instead of beams of light or radiation, these are actually high-speed subatomic particles racing through space at nearly the speed of light. Most of them are protons, the same building blocks found in the heart of every atom in your body, but flung across the universe with unimaginable force. Think of them less like rays of sunshine and more like microscopic bullets fired from the most violent places in the cosmos. Supernova, the explosive deaths of massive stars, are some of the best-known cosmic particle accelerators, flinging protons and atomic nuclei outward with enough energy to cross entire galaxies. But they're not the only source. Colliding neutron stars, active galactic nuclei, and even the superheated edges of black holes contribute to this invisible hail of high-speed particles. What makes them so fascinating isn't just their speed, it's the sheer scale of their journeys. Some of these particles have been traveling for millions, even billions of years before they reach us. They're cosmic time capsules carrying fingerprints of the events that launched them, and when they finally slam into Earth's atmosphere, they trigger cascades of secondary particles, creating showers of energy detectable by observatories here on the ground. So why does this distinction matter? Because calling them rays makes them sound harmless, like a beam of light. In reality, cosmic rays are a relentless bombardment, a reminder that the universe is far from empty. It's a storm of invisible projectiles, each one a tiny piece of some distant catastrophe. And every one that hits us is a messenger telling a story about the extremes of space. On a perfectly ordinary morning in October 1991, a cosmic particle smashed into Earth's atmosphere with so much energy it left physicists speechless. Detected by the University of Utah's Fly's Eye experiment, this single subatomic traveler carried the punch of a fastball hurtling at 60 miles per hour, except it was smaller than an atom. The shock wasn't just its power, but the sheer impossibility of its existence. Scientists dubbed it the "Oh my God" particle, a name that perfectly captured their stunned disbelief. Here's why it shattered expectations. Based on our understanding of physics, particles this energetic shouldn't survive intergalactic travel. The universe is filled with cosmic microwave background radiation, the faint afterglow of the Big Bang, which should act like friction, slowing high-energy particles over long distances. Yet this one arrived with enough force to suggest it had traveled hundreds of millions of light-years virtually untouched. It was like finding a bullet that had been fired across an ocean, only to hit its target with undiminished speed. Theories scramble to explain its origin. Some suggest it was flung our way by a nearby active galactic nucleus, where a supermassive black hole's magnetic fields act like a cosmic slingshot. Others propose even wilder sources, like colliding galaxy clusters or defects in the fabric of space-time itself. But decades later, no single explanation fits perfectly. What we do know is that "Oh my God" particles are vanishingly rare. Only a handful have ever been detected, and each one forces us to reconsider the limits of nature's particle accelerators. Perhaps most unsettling is what these particles imply about the universe's hidden violence. If something out there can hurl matter with such incomprehensible force, what other extreme phenomena are we missing? Every "Oh my God" particle is a humbling reminder. The cosmos operates on scales that dwarf human imagination, and sometimes all we can do is stare at the data and whisper, what on earth or beyond it could have done this? Here's something that bends the rules of physics without actually breaking them. Cosmic particles that outrace light itself, at least light traveling through air. While nothing can surpass light's speed in a vacuum, when these high-energy particles slam into Earth's atmosphere, they momentarily move faster than light does in that dense medium. The result, a mesmerizing blue glow known as Cherenkov radiation, nature's version of a sonic boom for light. Picture a fighter jet breaking the sound barrier, creating a shockwave you can hear. Now imagine a subatomic particle doing the same thing, but with light. As these particles, often neutrinos or other cosmic ray byproducts, zip through the atmosphere, they push aside molecules, polarizing them in a way that releases photons. This sudden burst of energy manifests as an eerie blue flash, visible in specialized detectors like the Super Kamiok and Observatory in Japan. It's as if the universe is leaving a luminous fingerprint, a fleeting signpost of invisible forces at work. Neutrinos, those ghostly particles that barely interact with matter, are prime culprits here. When one of these elusive particles finally collides with an atom in our atmosphere or even deep underground in water-filled detection tanks, the resulting particle shower can produce Cherenkov light. Scientists use this glow like a cosmic breadcrumb trail, tracing neutrinos back to their origins, whether that's a supernova in another galaxy or the fiery heart of a distant quasar. What's truly mind-bending is how this phenomenon tricks our intuition. We're taught light is the universe's ultimate speed limit, and it is but only in empty space. Light slows down when passing through air, water, or glass, while these ultra-fast particles don't hit the brakes. For a split second, they become cosmic speedsters, outpacing photons in their medium and leaving behind that signature blue pulse. It's a reminder that even the most fundamental laws of physics have layers, and sometimes the most extraordinary discoveries come from watching particles break what we thought were the rules. Not all cosmic rays are created equal. Some are galactic wanderers from deep space, while others are local products of our own sun's fury. Galactic cosmic rays are the heavyweight champions of particle energy, protons and atomic nuclei accelerated to nearly light speed by distant supernova or active black holes. These intergalactic travelers can pack billions of times more energy than anything our sun produces, enduring journeys so long that some may predate Earth itself. Then there are solar cosmic rays, the sun's temper tantrums made manifest. Born from solar flares or coronal mass ejections, these particles are slower and less energetic but far more numerous, and when the sun is in an active phase, they can flood our planet's magnetic field like a storm surge. The key difference lies in their origins. Galactic cosmic rays come from the universe's most violent events, colliding neutron stars, quasars, or the shockwaves of dying stars. They're the lone survivors of cosmic catastrophes, their paths twisted by magnetic fields across millions of light years. Solar cosmic rays, meanwhile, are homegrown. When the sun's magnetic fields snap and reconnect, they catapult protons outward in eruptions that can reach Earth in minutes. While a single galactic cosmic ray might carry the energy of a speeding baseball, a solar flare can unleash trillions of lower energy particles in a single burst. Solar activity acts like a cosmic dimmer switch for Earth's exposure. During periods of high solar activity, the sun's increased magnetic field and solar wind actually deflect some galactic cosmic rays, like an umbrella shielding us from interstellar rain. But this comes at a cost. Those same solar storms bombard us with their own particles, which can disrupt satellites, power grids, and even astronaut safety. During solar minimums, the umbrella folds, allowing more galactic cosmic rays to penetrate while solar particles taper off. It's a delicate balance, one that reminds us how connected we are to the sun's rhythms and how vulnerable. Here's the irony: the sun, our protector and provider, also becomes a temporary threat when it's most active. Astronauts on the International Space Station monitor solar weather closely, knowing that a single flare could expose them to radiation levels equivalent to years of natural background dose. Meanwhile, galactic cosmic rays are the slow, steady background noise of the universe, less intense in bursts but relentless over time. Together, they paint a picture of a solar system caught between two kinds of storms, one local and familiar, the other ancient and alien, both whispering secrets about the forces that shape our cosmic neighborhood. Somewhere between the crash of a hailstorm and the whisper of a single raindrop, cosmic rays reveal a pattern that shouldn't exist, a sudden shift in their numbers at two precise energy thresholds. Scientists call them the knee and the ankle, not because they're body parts, but because the graph of cosmic ray energies takes sharp turns at these points, like a runner changing pace. At around 10 to the 15th electron volts, the number of cosmic rays drops dramatically, the knee. Then, at 10 to the 18th electron volts, the decline slows again, the ankle. These aren't just quirks of data, they're cosmic road signs pointing to fundamental shifts in how these particles travel and where they come from. What causes the knee? One leading theory blames our galaxy's magnetic fields. Up to this energy level, most cosmic rays are thought to originate within the Milky Way, accelerated by supernova remnants or pulsars. But beyond the knee, the particles carry so much energy that the galaxy's magnetic grip can't hold them. They break free, escaping into intergalactic space like sparks from a bonfire. This would explain why we detect fewer of them. The ones that stay are the exception, not the rule. The ankle, meanwhile, hints at something even stranger. At these ultra-high energies, the cosmic ray count levels off slightly, suggesting a new population of particles is stepping in. Some researchers think these might come from outside our galaxy, hurled at us by active supermassive black holes or colliding galaxy clusters. Others propose they're the remnants of long-dead stars in neighboring galaxies, re-accelerated by shockwaves in the interstellar medium. Here's where it gets eerie: the highest energy cosmic rays, the ones above the ankle, shouldn't reach us at all. The universe is filled with the cosmic microwave background, a sea of low-energy photons left over from the Big Bang. Particles with energies beyond 10 to the 18th electron volts should collide with these photons, losing energy over distances as short as 100 million light-years. Yet they arrive anyway, This is the Greisen-Zatzepin-Kuzmin limit or GZK cutoff, a theoretical barrier that some cosmic rays seem to ignore. Either they're coming from much closer than we thought, or something out there is revving them up again mid-journey, like a cosmic pit stop we can't yet explain. The knee and ankle aren't just plot twists in the story of cosmic rays, they're clues to the universe's hidden mechanics. Every time we detect a particle in these energy ranges, it's like intercepting a coded message about the forces that shaped its journey. And with each new observation, we get a little closer to cracking the cipher. When a single high-energy cosmic ray, something as small as a proton, hits Earth's atmosphere at nearly the speed of light, it doesn't arrive quietly. It triggers an avalanche, a chain reaction so vast it can carpet an area the size of a city with secondary particles. Scientists call these explosions of subatomic debris air showers, and they're among the most spectacular natural particle physics experiments happening right above our heads. The moment that lone cosmic particle collides with an air molecule, it shatters into a spray of new particles, pions, muons, electrons, each carrying a fraction of the original energy. These newcomers then slam into other air molecules, creating even more particles, and the process repeats in a geometric explosion. Within microseconds, a single proton can spawn billions of secondary particles, all racing toward the ground in a widening disk. The largest air showers ever detected have contained more than 10 billion particles, spread across several square miles, like an invisible firework bursting in slow motion. What makes air showers so fascinating is how they mimic humanity's most advanced technology. Particle accelerators like the Large Hadron Collider smash protons together to study the building blocks of matter. But nature has been doing this for billions of years, using the atmosphere as its collision chamber. The difference: our machines create controlled collisions in vacuum-sealed tunnels, while cosmic rays turn the sky itself into a chaotic, sprawling accelerator. The numbers are staggering. A typical high-energy cosmic ray with an energy around 10 to the 15th electron volts might produce a shower with 1 million particles by the time it reaches the ground. But the real monsters, those ultra-high-energy cosmic rays, can generate showers with particles numbering in the tens of billions. These are so rare that scientists might detect only 1 per square mile per century, but when they strike, they leave unmistakable fingerprints in detectors scattered across deserts or buried in ice. Here's the twist: most of these particles never make it to the surface. The atmosphere acts as a shield, absorbing the bulk of the shower's energy. By the time the cascade reaches the ground, it's often just muons, heavy cousins of electrons, and a few other survivors that penetrate buildings, rock, even deep underground. That's why observatories like the Pierre Auger Array in Argentina use vast fields of detectors to catch these remnants, piecing together the shower's original energy and direction like cosmic forensic scientists. Air showers aren't just astrophysical curiosities, they're teaching us about the limits of particle physics. Some showers contain muons in numbers that defy current models, hinting at gaps in our understanding of how matter behaves at energies far beyond what we can recreate on Earth. Others arrive at angles that suggest they're being bent by magnetic fields we can't yet map. Every shower is a snapshot of an invisible universe, one where particles rain down in numbers and patterns we're only beginning to decode. The next time you look up at a clear sky, remember, it's not empty. It's a battlefield where microscopic projectiles from across the cosmos are exploding in silent, invisible bursts, each one a testament to the universe's relentless energy. And somewhere overhead, right now, another air shower might be unfolding. A fleeting storm of particles born from a single speck of stardust, traveling billions of years just to meet its end in the thin veil of our atmosphere. Among the invisible survivors of cosmic ray air showers, muons stand out as nature's most persistent penetrators. Born from the decay of pions in the upper atmosphere, these heavy, unstable particles behave like overcharged electrons, except they're 200 times more massive and can plow through solid rock like it's barely there. While most secondary particles from air showers get absorbed by the atmosphere, muons barrel onward, reaching depths of hundreds of meters underground or even the darkest trenches of the ocean. Their secret, unlike other particles, muons rarely interact with matter electromagnetically. They slip between atoms almost undisturbed, like ghosts walking through walls, carrying whispers of cosmic collisions from miles above. Scientists first realized muons could reach underground in the 1930s when detectors buried deep in mines kept picking up signals. Today, we know these particles are so relentless they've been detected nearly a mile beneath the Earth's surface. Nuclear reactors use this property to their advantage. Muon tomography, a technique that tracks how muons scatter as they pass through dense materials, can peer inside structures too hazardous or massive for conventional X-rays. After the Fukushima disaster, researchers employed muon imaging to map melted fuel inside reactor cores without risking human exposure. But perhaps the most fascinating application lies in archaeology. In 2017, a team scanning Egypt's Great Pyramid of Giza discovered a hidden void above the Grand Gallery using cosmic ray muons. By placing detectors inside the pyramid, they mapped how muon flux varied across the structure. More muons meant less dense stone, revealing chambers untouched for millennia. Similar projects have scanned volcanic chambers, Mayan pyramids, and even potential tunnels beneath ancient temples, all without lifting a shovel. The particles that once seemed like background noise are now precision tools, turning the planet itself into a giant scanner powered by the cosmos. Muons also solve mysteries underwater. When neutrino observatories like Antares in the Mediterranean or Baikal-GVD in Siberia hunt for elusive neutrinos, they first have to filter out muons particles that mimic neutrino signals but arrive in far greater numbers. By studying how muons lose energy as they traverse water, physicists calibrate their instruments, separating cosmic noise from the rare neutrino interactions they're chasing. Even ice-bound detectors at the South Pole rely on muon data to fine-tune their search for particles from deep space. What's remarkable isn't just their penetrating power, it's their duality. Muons are both messengers and obstacles, cosmic relics and practical tools. They remind us that the universe's most ordinary-seeming phenomena can become extraordinary when viewed through the right lens. And somewhere beneath your feet right now, muons from a cosmic ray that struck the atmosphere days ago are still traveling, silent and unseen, their journey a testament to the invisible forces threading through our world. Stretching across 3,000 square kilometers of Argentina's Mendoza province, the Pierre Auger Observatory doesn't just study cosmic rays, it turns an entire landscape into a scientific instrument. Named after the French physicist who pioneered cosmic ray research, this vast array is humanity's most ambitious attempt to catch the universe's highest energy particles in action. Unlike traditional telescopes that point skyward, Auger's detectors sprawl across the Pampa Amarilla, a high-altitude desert where the thin, dry air offers minimal interference to incoming cosmic rays. The observatory's secret weapon, 1,600 water tanks, each the size of an Olympic swimming pool starting block, spaced a mile apart like a grid of giant dominoes. These aren't ordinary containers, they're lined with ultra-sensitive light detectors that pick up the faint blue glow of Cherenkov radiation, the telltale sign of a cosmic ray air shower. When a high-energy particle strikes the atmosphere above the array, the resulting cascade of secondary particles triggers a synchronized flash across multiple tanks, allowing scientists to triangulate the shower's origin with pinpoint accuracy. It's like turning the Earth's surface into a colossal camera, capturing snapshots of invisible particle explosions, but water tanks only tell half the story. Auger complements its ground array with 24 fluorescence telescopes strategically placed on the observatory's perimeter. These detect the ultraviolet light emitted by nitrogen molecules when air shower particles excite them, a faint, flickering glow invisible to the human eye but unmistakable to Auger's instruments. By combining both detection methods, the observatory achieves something remarkable. It can reconstruct not just the direction of incoming cosmic rays, but their energy and composition too. The tanks measure the shower's footprint on the ground, while the telescopes trace its development through the atmosphere, like watching a firework burst in reverse. The scale of data collection here dwarfs most scientific projects. Every tank operates autonomously, powered by solar panels and connected via wireless networks to a central hub. When a cosmic ray event occurs often just a few times per year for the highest energy particles, the entire array springs to life within nanoseconds, recording terabytes of data on particle densities, arrival times, and energies. Then comes the real challenge, sifting these cosmic fingerprints for clues about their origins. Ultra-high-energy cosmic rays are so rare that Auger has catalogued barely 30 in 2 decades, each one a potential Rosetta Stone for understanding the universe's most violent accelerators. What makes Auger revolutionary isn't just its size, it's its ability to answer questions that smaller detectors couldn't touch. Before Auger, scientists debated whether the highest energy cosmic rays came from our galaxy or beyond. The observatory settled this by mapping their arrival directions, revealing clusters that point toward active galactic nuclei in the distant universe. It also confirmed something startling. At energies above 8 times 10 to the 18th electron volts, cosmic ray numbers drop off a cliff, evidence of the GZK cutoff, that theoretical limit imposed by collisions with cosmic microwave background photons. Yet for all its sophistication, Auger has deepened mysteries as much as it's solved them. Some ultra-high-energy events arrive in groups from seemingly empty regions of space with no obvious source. Others have compositions that defy expectations, hinting at unknown particle acceleration mechanisms. And then there's the enigma of super-heavy cosmic rays nuclei like iron or even heavier elements accelerated to impossible speeds, challenging theories about how black holes or merging galaxies could launch such dense projectiles. The observatory's design continues to evolve. Recent upgrades added scintillator detectors atop each water tank, helping distinguish muons from other shower particles, a crucial step in identifying cosmic ray types. Future expansions might include radio antennas to capture another shower byproduct, shortwave pulses emitted when electrons in the cascade are deflected by Earth's magnetic field. These innovations ensure Auger remains at the forefront of what scientists call multi-messenger astrophysics, the quest to understand cosmic phenomena by studying every detectable signal they produce. Standing at Auger's control center, surrounded by real-time data feeds from across the array, you begin to grasp the project's true brilliance. It transforms randomness into revelation. Each water tank flash, each ultraviolet streak in the night sky, is a breadcrumb leading back to events of unimaginable violence, supernova, quasar jets, perhaps even phenomena we've yet to name. In catching these whispers from the cosmic dark, the observatory does more than study particles. It turns the entire planet into a witness to the universe's most powerful explosions. And somewhere out there, another ultra-high-energy cosmic ray is streaking toward Earth, destined to leave its mark in Auger's waiting tanks, carrying secrets we're only beginning to decipher. Deep in the silicon heart of your smartphone or laptop, an invisible war rages: cosmic rays versus computer code. These high-energy particles don't just pass through our atmosphere. They occasionally strike microchips with enough force to flip individual bits of data from 0 to 1 or vice versa. It's called a single event upset, and while it sounds like a minor glitch, the consequences can range from amusing to catastrophic. In 1996, a commercial airliner flying from London to Rome experienced a sudden, uncommanded roll that sent it plummeting 2,000 feet before pilots regained control. Investigators traced the fault to a cosmic ray flipping a single bit in the aircraft's flight control computer, a 1 in a billion chance that temporarily turned advanced avionics into a chaotic mess. The phenomenon isn't limited to aviation. In 2003, a voting machine in Belgium recorded a bizarre 4,200 extra votes during an election, a malfunction later attributed to cosmic ray interference. Even space agencies aren't immune. NASA engineers designing the Curiosity rover's onboard computers had to account for constant cosmic ray bombardment on Mars, where the thin atmosphere offers less protection than Earth. Their solution: triple redundant systems that vote on every calculation, ensuring a single flipped bit won't send the rover driving off a cliff. What makes these events so insidious is their randomness. Unlike software bugs or hardware failures, cosmic ray bit flips leave no trace, no overheating components, no corrupted code. They're the digital equivalent of a ghost touching your keyboard. Modern electronics have grown so miniaturized that a single high-energy particle can disrupt transistors just nanometers wide. The smaller the tech, the bigger the risk. A cosmic ray strike on a modern 7-nanometer chip is like dropping a pebble into a swimming pool. The ripples can spread far beyond the initial impact point, causing cascading errors. Tech companies have quietly been waging this battle for decades. Server farms for companies like Google and Amazon now use error-correcting code memory that can detect and fix single-bit flips on the fly. Some satellite operators even deliberately underpower their electronics, a trick that makes transistors less susceptible to cosmic ray disruption. But as we push computing to its physical limits, whether in self-driving cars or quantum systems, the stakes keep rising. When a single cosmic ray can derail an algorithm deciding whether to brake or accelerate, the line between physics glitch and real-world danger blurs. Perhaps the most famous cosmic ray mishap happened during a 1998 presidential primary in South Carolina. A voting machine mysteriously subtracted 1,000 votes from a candidate overnight. Forensic analysis pointed not to hacking or human error, but to a cosmic particle striking the machine's memory chip. It's a reminder that no matter how advanced our technology becomes, we're still at the mercy of particles older than the solar system, silent, invisible, and utterly indifferent to the chaos they sometimes leave in their wake. Imagine a solar storm so powerful it can reroute international flights, not because of turbulence, but because of invisible radiation spikes. This is space weather, a real-time cosmic forecast driven by the sun's tantrums, and it directly controls how many high-energy particles rain down on Earth. When the sun erupts with a coronal mass ejection, it doesn't just paint the skies with auroras, it temporarily shields us from galactic cosmic rays. The ejected plasma carries the sun's magnetic field outward, creating a protective bubble that deflects some interstellar particles. But there's a catch. These same solar storms bombard us with their own high-energy protons, turning near-Earth space into a radiation minefield. Airlines track these events like hurricanes. At cruising altitudes, where the atmosphere's protective shield is thinner, passengers and crew receive doses of cosmic radiation comparable to chest X-rays, harmless in small amounts but concerning for frequent flyers. During solar storms, radiation levels can spike tenfold in minutes. That's why carriers like Delta and Lufthansa employ space weather forecasters, rerouting polar flights to lower latitudes when solar protons flood Earth's magnetic field. A single transatlantic flight during a severe storm could expose someone to a week's worth of natural background radiation in hours. Pilots face an even starker calculus. The FAA classifies flight crews as radiation workers alongside nuclear plant technicians because their annual exposure rivals some occupational limits. Studies show long-haul aviators have slightly elevated risks of certain cancers, a statistical whisper traced back to decades of cruising through the thin, particle-filled air at 35,000 feet. Modern aircraft now carry neutron monitors, the same detectors used in cosmic ray observatories, to alert crews when radiation exceeds safe thresholds. Here's the irony: the sun's fury has a silver lining. Between solar maximums, those 11-year peaks when the sun is most active, its expanded magnetic field acts like a cosmic broom, sweeping some galactic rays away from the inner solar system. Earth's radiation environment during these periods is paradoxically calmer, despite the increased solar outbursts. But during solar minimums, when the sun's activity wanes, galactic cosmic rays penetrate deeper, creating a steady drizzle of high-energy particles that's harder to predict than solar storms. Scientists now treat Earth's atmosphere like a giant radiation meter. By monitoring muons, those penetrating particles born from cosmic ray collisions, they can detect real-time changes in space weather. Underground detectors in places like the UK's Bowlby mine watch muon flux drop when solar storms arrive, a phenomenon called the muon deficit. It's a reminder that the sun doesn't just give us light and heat. It's the conductor of an invisible orchestra, tuning the cosmic rays that constantly surround us. For astronauts, these fluctuations aren't academic, they're life or death variables. The International Space Station orbits within Earth's magnetic shield, but moon-bound crews or Mars colonists won't have that luxury. NASA's Artemis program now schedules lunar missions around solar forecasts, aiming to minimize exposure during periods of expected galactic ray peaks. Future moon bases might bury habitats under meters of regolith, turning lunar soil into a makeshift cosmic ray bunker. The next time you board a plane, look out the window at that seemingly empty sky. It's not just air out there, it's a dynamic frontier where forces older than our solar system battle the sun's temper, and where a single solar flare can rewrite the rules of radiation exposure for everyone, from pilots to passengers to the satellites guiding your flight path. Space weather isn't some distant abstraction, it's the silent partner in every high-altitude journey, a reminder that we're all flying through a cosmic storm, whether we notice it or not. Every second you stand still, cosmic rays turn your body into an unwitting particle detector. On average, 10,000 high-energy particles from distant galaxies zip through you, bouncing off atoms in your skin, darting between cells, even passing straight through your bones. That's 600,000 cosmic ray interactions every minute, 36 million per hour, all completely unnoticed. This bombardment isn't dangerous, it's been happening since life began, but it reveals something astonishing about our connection to the cosmos. Let's break down the numbers. Most of these particles are muons, those heavy electron cousins from atmospheric showers, arriving at a rate of about 1 per square centimeter per minute at sea level. Go higher, say, a mountain city like Denver, and that rate triples. At commercial flight altitudes, the particle flux jumps to 300 times surface levels, which is why airline crews receive the highest annual radiation doses of any civilian profession. Even nestled underground, you're not completely shielded. Muons penetrate hundreds of meters of rock, ensuring nowhere on Earth is truly particle-free. The total annual dose from cosmic rays averages 0.3 millisieverts, roughly 10 chest X-rays spread over a year, but geography alters this significantly. Residents of Tibet or the Andes, where thinner atmosphere provides less shielding, absorb nearly double the cosmic radiation of people at sea level. Conversely, a week spent in New York subway tunnels could have your normal exposure. The variations don't stop there. Earth's magnetic field funnels more particles toward the poles, making Arctic communities inadvertent cosmic ray hotspots. What's remarkable isn't just the quantity, but the origins. Some muons passing through you right now were created by cosmic rays that left their sources before Earth formed. The protons that spawned them might have circled the Milky Way for eons, trapped by galactic magnetic fields before finally colliding with our atmosphere. Others could be fresh arrivals from recent supernova in nearby spiral arms. Every particle carries a fragment of cosmic history, making your body a living archive of the universe's most violent events. Scientists track these exposures with eerie precision. Dosimeters placed in astronaut training facilities, nuclear submarines, and even deep mines confirm cosmic rays contribute more to our natural radiation background than the Earth's radioactive rocks. There's even evidence these particles play a role in evolution. Their ability to cause subtle DNA mutations may have influenced life's genetic diversity over billions of years. Yet for all this constant particle rain, the risk is vanishingly small. You'd need centuries of normal exposure to match the radiation from one CT scan. The human body has evolved exquisite repair mechanisms to handle this background damage, fixing most cosmic ray-induced DNA breaks within hours. It's a delicate equilibrium. We exist in a particle storm, but one so diffuse it's woven seamlessly into the fabric of life. Next time you feel an unexplained shiver, consider this. Somewhere in your body, a muon from a galaxy far away just deposited its energy and vanished. You're not just living on Earth, you're a transient intersection point for particles older than the Sun, a walking testament to the universe's invisible conversation. The energy packed into a single high-energy cosmic ray defies everyday intuition. If you could somehow bottle that energy as heat, that tiny particle would blaze at over 10 million degrees. That's not an exaggeration. The most extreme cosmic rays carry kinetic energy equivalent to temperatures hotter than the solar core, where nuclear fusion rages at 15 million degrees. Yet here's the twist: these particles aren't hot in the conventional sense. They don't melt through detectors or vaporize everything they touch, because temperature at this scale becomes a measure of motion rather than thermal chaos. Picture a proton accelerated to 99.9999% the speed of light, so close to light speed that relativistic effects stretch its mass exponentially. At these velocities, what we perceive as temperature transforms into raw kinetic energy, concentrated into a volume smaller than an atom. If that same energy were spread across a visible object, it would indeed rival the Sun's interior. But cosmic rays don't dissipate their energy like a burning log. They deliver it like a bullet, transferring immense force upon collision while leaving their surroundings cold. This paradox, unimaginable energy density without heat, is why cosmic rays baffled early researchers. When Victor Hess discovered them in balloon experiments over a century ago, he noticed radiation levels increasing with altitude, proving the particles weren't terrestrial. Today, we know some carry energies exceeding 100 exaelectron volts, equivalent to a baseball pitch compressed into a subatomic speck. The Sun's core seems almost placid by comparison. Its heat emerges from countless gentle collisions between particles, while a cosmic ray's fury comes from a single near-light-speed impact. The comparison gets even stranger when you examine origins. Solar core temperatures are sustained by gravity's crush, forcing hydrogen nuclei together until they fuse. Cosmic rays, on the other hand, owe their energy to electromagnetic chaos, black holes spinning magnetic fields like cosmic slingshots, or supernova shockwaves acting as natural particle accelerators. These mechanisms don't just match stellar temperatures, they surpass them. The Crab Nebula's pulsar, for instance, whips particles to energies that would correspond to trillions of degrees if thermalized. What does this mean for us? Fortunately, very little. A cosmic ray's extreme temperature is fleeting, dissipated harmlessly when it collides with air molecules. But for physicists, these particles are living proof that the universe operates energy scales beyond anything we can replicate. The Large Hadron Collider, humanity's most powerful accelerator, tops out at energies equivalent to about 10 trillion degrees, a mere fraction of what nature achieves routinely in deep space. So next time you feel the warmth of sunlight, remember, somewhere out there, invisible particles are screaming through the void with energies that dwarf the sun's furnace, carrying whispers of forces so violent they make stellar cores seem tame. And every second they rain down through the atmosphere, a silent reminder that the universe's true extremes aren't in stars, but in the subatomic shrapnel of its most catastrophic explosions. Cosmic rays might be shaping Earth's climate in ways we're only beginning to understand, not by heating the atmosphere, but by potentially seeding clouds. It's a theory that sparked fierce debate among scientists. Could these high-energy particles from deep space influence weather patterns by altering cloud cover? The idea hinges on a chain reaction that starts when cosmic rays collide with molecules in our atmosphere, creating ions that act as microscopic anchors for water vapor. These charged particles could help water droplets cluster, forming the nuclei around which clouds condense. More cosmic rays might mean more clouds, and more clouds could reflect sunlight back into space, cooling the planet. The hypothesis gained traction in the late 1990s when Danish physicist Henrik Svensmark noticed a striking correlation between cosmic ray intensity and low-altitude cloud cover over several solar cycles. When the sun's magnetic activity weakens during solar minimums, more cosmic rays punch through to Earth's atmosphere, and curiously, cloud cover tends to increase. Svensmark's experiments in cloud chambers showed that ionized particles, like those created by cosmic rays, do indeed promote droplet formation. If this effect scales up globally, it would mean cosmic rays act as a cosmic thermostat, with the sun's magnetism indirectly dialing Earth's cloud cover up or down. Not everyone is convinced. Critics point out that while lab experiments demonstrate the ionization process, its real-world impact remains murky. Satellite data over the past 2 decades shows conflicting trends. Some studies find a correlation between cosmic rays and cloud cover, while others detect no significant link. The physics of cloud formation is staggeringly complex, involving everything from ocean bacteria to industrial pollution, making it hard to isolate cosmic rays as a dominant factor. Then there's the energy problem. The particles involved in cosmic ray-induced ionization carry far less energy than typical atmospheric processes, raising questions about whether they could truly drive large-scale climate effects. One of the biggest challenges is untangling cosmic rays from other variables. Volcanic eruptions, for example, spew particles that also seed clouds, while human-made aerosols from burning fossil fuels can either block or enhance cloud formation depending on their composition. The Pacific Ocean's El Niño cycles shuffle heat and moisture globally, further mudding the signal. Even if cosmic rays do influence clouds, their effect might be drowned out by these louder climate players. Yet the theory refuses to fade. Some researchers argue that even a small cosmic ray influence could act as an amplifier for other climate mechanisms, like a subtle nudge that tips the balance toward cooling or warming. Others speculate that during Earth's distant past, when the solar system passed through regions of the galaxy with higher cosmic ray densities, these particles might have triggered ice ages. There's even evidence linking cosmic ray spikes to periods of increased lightning activity, another atmospheric phenomenon that could feed back into cloud dynamics. The stakes are high. If cosmic rays significantly affect cloud formation, it would force us to rethink both climate models and our understanding of the sun's role in Earth's temperature shifts. It wouldn't negate human-driven climate change. Greenhouse gases still trap heat regardless of cloud cover, but it could revise predictions about how sensitive the planet is to various influences. For now, the jury's out. Projects like Cloud at CERN are simulating atmospheric conditions with particle beams, trying to pin down whether cosmic rays are mere bystanders or silent architects of the skies above us. What's clear is that the universe never stops surprising us. Particles born in distant supernova might be quietly tweaking the very fabric of our weather, threading a connection between stellar explosions and the drizzle outside your window. Whether that connection is real and how strong it is remains one of climate science's most tantalizing unsolved puzzles. Most telescopes stare upward, searching the heavens for clues, but the High-Altitude Water Cherenkov Observatory, or HAWK, does something radically different. Perched on the slopes of Mexico's Sierra Negra volcano at 13,000 feet, this array of 300 water-filled tanks doesn't look skyward at all. Instead, it watches the ground, waiting for flashes of blue light triggered by particles that come from below. It sounds like science fiction, but HAWK downward gaze reveals one of astrophysics' most ingenious workarounds, catching gamma rays not by detecting them directly, but by spotting the aftermath of their destruction. Here's how it works. When a high-energy gamma ray, often billions of times more energetic than visible light, collides with Earth's upper atmosphere, it annihilates itself in a burst of matter and antimatter. That explosion spawns a cascade of secondary particles screaming toward the ground at nearly light speed. As these particles plunge through HAWK water tanks, they momentarily outpace light in that medium, creating shockwaves of blue Cherenkov radiation. Each tank acts like a camera pixel, capturing the direction, energy, and timing of these flashes. By stitching together signals across the entire array, scientists can trace the shower backward, reconstructing the gamma ray's original path with surprising precision. The real stroke of genius lies in HAWK altitude. Most cosmic ray detectors sit at lower elevations where air showers are nearly spent. But at Sierra Negra's thin air heights, HAWK intercepts showers earlier in their development, catching more particles before they disperse or decay. It's like standing closer to a fireworks launch. You see the explosion's full structure rather than just the fading embers. This vantage point lets HAWK monitor 2/3 of the sky at once, day and night, spotting gamma rays from sources as diverse as supernova remnants, pulsars, and even the supermassive black hole at our galaxy's core. Why does pointing downward work? Because gamma rays never actually reach the ground. Unlike cosmic rays, which are sturdy protons or atomic nuclei that can penetrate to Earth's surface, gamma rays are photons, packets of pure energy that obliterate themselves on contact with air molecules. By the time their particle showers hit HAWK, the original gamma ray is long gone, but its energy lives on in the chaotic aftermath. This indirect approach turns the entire atmosphere into a giant gamma ray detector, with HAWK reading the fingerprints these particles leave behind. Some of HAWK's most startling discoveries come from its ability to spot extended sources. Traditional gamma-ray telescopes struggle to map huge structures like the Fermi bubbles, gigantic lobes of energy stretching 25,000 light-years above and below the Milky Way. But HAWK's wide field of view and constant monitoring have revealed these and other vast features in unprecedented detail, showing how gamma rays trace the galaxy's largest particle accelerators. The observatory has even detected mysterious hotspots of ultra-high-energy gamma rays with no obvious source, hinting at cosmic engines we've yet to identify. The next time you see a telescope, remember, sometimes the best way to study the cosmos isn't by looking up, but by watching the ground beneath your feet. Every flash in HAWK tanks is a cosmic message relayed through an atmospheric game of telephone, a reminder that even when the universe destroys its own messengers, their echoes still reach us if we know where to listen. Some cosmic rays carry energies so immense they couldn't possibly have originated within our galaxy. These intergalactic interlopers, packing over 10 to the 18th electron volts, enough to power a small light bulb for several seconds if harnessed, travel millions or even billions of light years before reaching Earth. Their existence poses a tantalizing mystery. What cosmic behemoths could launch particles across such unfathomable distances without dissipating their energy along the way? The prime suspects lie in the hearts of distant galaxies, where supermassive black holes spin like dynamos, warping space-time itself into particle accelerators of unimaginable scale. Active galactic nuclei, or AN, are leading candidates. These are galaxies with cores so luminous they outshine the rest of their stars combined, powered by black holes millions to billions of times the mass of our Sun. As these black holes devour surrounding matter, they generate jets of plasma stretching thousands of light years, threaded with magnetic fields strong enough to whip particles to near light speeds. Picture a natural version of the Large Hadron Collider, but scaled up to galactic proportions where magnetic turbulence acts like a cosmic pinball machine, repeatedly flinging protons and nuclei outward with ever-increasing energy. Some models suggest particles could gain energy incrementally over centuries as they bounce between shock fronts in these jets, like a surfer catching wave after wave until they're hurled into intergalactic space. Yet AGNs aren't the only extragalactic suspects. Colliding galaxy clusters, where hundreds of galaxies smash together in slow motion over cosmic time, create shockwaves that might accelerate particles to similar extremes. Then there's the enigmatic class of objects called blazars, AGNs whose jets happen to point directly at Earth, amplifying their apparent brightness. When the Pierre Auger Observatory traced the arrival directions of ultra-high-energy cosmic rays, several pointed toward known blazars, including one 300 million light-years away in the constellation Ursa Major. It's like finding a bullet with a return address stamped from halfway across the observable universe, but the plot thickens. Some of the highest energy cosmic rays arrive from seemingly empty regions of space. No galaxy clusters, just void. This could mean our maps of distant galaxies are incomplete, or it might hint at even stranger possibilities. Theoretical physicists have proposed exotic origins like cosmic strings, defects in space-time left over from the Big Bang, or decaying dark matter particles releasing bursts of energy. Others speculate these particles might be relics from the universe's infancy, boosted to staggering speeds by primordial magnetic fields we can no longer detect. What makes extragalactic cosmic rays so extraordinary isn't just their energy, it's their survival. The universe is filled with the cosmic microwave background, a fog of low-energy photons that should sap the energy from ultra-high-speed particles over long distances, a phenomenon called the GZK cutoff. The fact that we detect these particles at all suggests they either come from relatively nearby within 100 million light-years, or something out there is re-energizing them mid-flight, like cosmic gas stations we've yet to discover. Every time one of these intergalactic projectiles strikes Earth's atmosphere, it carries encoded clues about the environments it traversed, the strength of intergalactic magnetic fields, the density of matter between galaxies, even the large-scale structure of the universe itself. They're more than just particles, they're forensic evidence from the most violent neighborhoods of the cosmos, and decoding their origins might rewrite our understanding of how energy flows across the tapestry of space and time. The universe has a speed limit not just for light but for cosmic rays too. In 1966, three physicists, Greisen, Zatsepin, and Kuzmin, calculated an absolute energy ceiling for cosmic particles traveling across intergalactic space. Their theory, now called the GZK cutoff, states that no cosmic ray should reach Earth with energies above 5 × 10⁻¹9 electron volts. The reason: a relentless cosmic drag force that's been at work since the dawn of time. Picture a marathon runner sprinting through a perpetual hailstorm. That's essentially what ultra-high-energy cosmic rays endure as they traverse the cosmos. The hailstorm in this analogy is the cosmic microwave background, the faint afterglow of the Big Bang that permeates every cubic inch of the universe. When a proton moving at near light speed collides with one of these low-energy photons, the interaction produces new particles, sapping the proton's energy. Over distances exceeding 100 million light-years, this process should bleed cosmic rays dry, capping their maximum detectable energy at the GZK limit. Yet here's the cosmic curveball. We've detected multiple particles that smash right through this theoretical barrier. The oh my god particle, with its staggering 300 × 10⁸ electron volts, was just the beginning. Observatories like the Pierre Auger Array have since catalogued dozens more ultra-high-energy events that defy the GZK cutoff. It's as if nature is thumbing its nose at our physics textbooks, leaving scientists scrambling for explanations. One possibility is that these particles aren't traveling as far as we think. If cosmic rays with energies beyond the GZK limit originate within our local supercluster of galaxies, within roughly 100 million light-years, they might not have journeyed long enough to hit the energy loss wall. The challenge: we don't know of many cosmic powerhouses nearby capable of producing such extreme particles. The Centaurus, a galaxy, an active galactic nucleus about 13 million light-years away, is a prime suspect, but its particle jets don't quite align with some of the detected events. Another theory takes a page from quantum mechanics. Protons at these insane energies might briefly forget their protons due to relativistic effects, transforming into exotic particles called delta resonances that interact less with the cosmic microwave background. It's like the cosmic ray puts on an invisibility cloak for part of its journey, slipping past photons that would otherwise slow it down. This quantum loophole could let particles preserve more energy over vast distances, though the math remains hotly debated. Then there's the wild-card explanation that the GZK cutoff isn't wrong, but incomplete. Some models suggest cosmic rays could get mid-flight boosts from turbulent magnetic fields in intergalactic space, effectively recharging their batteries. Others speculate that dark matter interactions or even flaws in Einstein's special relativity might play a role. The most radical proposals invoke entirely new physics, like extra dimensions subtly altering how particles lose energy across cosmic distances. What makes this mystery so compelling is its scale. Every ultra-high-energy cosmic ray that breaches the GZK limit carries implications far beyond astrophysics. It challenges our understanding of how energy, time, and space itself behave at extremes we can't replicate in any lab. These particles are more than anomalies. They're stress tests for the laws of physics as we know them. And with each new detection, the universe seems to be hinting that its rulebook might have chapters we haven't even glimpsed yet. For now, the GZK paradox remains one of cosmic ray astronomy's greatest puzzles. A theoretical wall that the universe keeps vaulting over with ease, leaving us to wonder whether we're missing something fundamental about the fabric of reality. Until we find more of these rule-breaking particles and trace their origins with certainty, the only thing we know for sure is this: the cosmos still holds cards it hasn't shown us. Among the cosmic rays bombarding Earth, there exists a particle so elusive it can pass through a light-year of lead without stopping. The neutrino. These ghostly subatomic particles, nearly massless and electrically neutral, barely interact with matter at all. Born in the nuclear furnaces of stars, supernova, and even from cosmic ray collisions in our own atmosphere, neutrinos outnumber all other fundamental particles in the universe combined. Yet despite their abundance, capturing one is like trying to catch smoke with your bare hands. What makes neutrinos so slippery? For starters, they ignore almost everything in their path. While a single cosmic ray proton might collide with atoms as it zips through the atmosphere, a neutrino could traverse the entire planet, or 1,000 planets, without bumping into a single nucleus. Their interactions are so rare that trillions pass through your body every second, leaving no trace. Even more baffling is their ability to shapeshift. Neutrinos come in 3 flavors: electron, muon, and tau, and they oscillate between these types as they travel, a quantum quirk confirmed by experiments that forced physicists to rewrite the standard model of particle physics. To catch these phantoms, scientists built one of the most unusual telescopes on Earth, IceCube. Buried deep in the Antarctic ice sheet, this detector consists of over 5,000 light-sensitive modules suspended along 86 cables, frozen into a cubic kilometer of pristine ice. When a neutrino finally does interact, an event so rare it might happen once per cubic kilometer per year, it produces a charged particle moving faster than light can travel through ice. The resulting blue Cherenkov radiation spreads through the frozen expanse, picked up by Ice Cube's sensors like a cosmic echo. The engineering behind Ice Cube is as audacious as the particles it hunts. Crews drilled holes 2.5 kilometers deep using hot water jets, then lowered the detectors before the ice refroze. The result is a natural particle trap where the ultra-clear ice acts as both detector medium and cosmic ray shield. Some of the Neutrinos' Ice Cube catchers have traveled uninterrupted for billions of years, carrying messages from quasars and colliding galaxies so distant their light hasn't reached us yet. Recent breakthroughs have turned these ghost particles into cosmic informants. In 2017, Ice Cube detected a neutrino with energy exceeding 200 tera-electron volts, a pinpoint that led astronomers to a blazing blazar 4 billion light-years away, its jet aimed directly at Earth. It was the first time a single neutrino was traced back to its source outside our galaxy, opening an entirely new window onto the high-energy universe. Now combined with gravitational wave detectors and gamma-ray telescopes, neutrino astronomy is revealing cosmic cataclysms invisible to traditional observatories. Perhaps most mind-bending is what neutrinos tell us about the universe's construction. The Big Bang should have created equal amounts of matter and antimatter, which would have annihilated each other, yet here we are. Neutrinos, with their subtle matter-antimatter asymmetries, might hold the key to why anything exists at all. These spectral particles, once thought impossible to study, have become indispensable guides to the universe's deepest secrets, proof that sometimes the most powerful messages come in the quietest whispers. In the eternal darkness of Antarctic ice, scientists hunt for ghost particles so fleeting they might as well be fragments of imagination. These aren't ordinary neutrinos, but trillion electronvolt monsters, packing energies that dwarf anything produced in Earth's most powerful accelerators. Detecting one is like finding a single specific grain of sand in all the world's deserts, but when it happens, the payoff is staggering. Clues to the most efficient particle accelerators in existence, hidden light years beyond our galaxy. The story begins in 2013 when Ice Cube, the frozen sentinel buried beneath the South Pole, caught two neutrinos with energies exceeding 1 peta-electronvolt each. Dubbed Bert and Ernie, these were no ordinary particles. Their energy levels suggested origins in cosmic environments so extreme, even supernova couldn't explain them. Then came Big Bird in 2014, a 2.3 peta-electronvolt neutrino so powerful, its discovery paper called it the most energetic neutrino ever observed. These weren't just random detections, they were cosmic postcards from places where matter is shredded and reassembled at energies we can scarcely comprehend. What makes these neutrinos so revealing is their indifference to magnetic fields. Unlike charged cosmic rays, which zigzag unpredictably through interstellar space, neutrinos travel in near-perfect straight lines from their birthplaces. Trace their paths backward, and you find their source with pinpoint accuracy, a feature astronomers exploited in 2017 when a high-energy neutrino led them straight to a blazar named TXS 0506 plus 056, 4 billion light-years away. This marked the first time humanity had identified a specific object outside our galaxy as a cosmic ray factory, using nothing but an invisible, nearly massless particle as a guide. The sheer violence required to create trillion electronvolt neutrinos boggles the mind. In blazars, supermassive black holes funnel matter into jets traveling at 99% light speed. Protons in these jets collide with photons or other particles, creating pions that decay into neutrinos. It's a multi-step particle assembly line operating on galactic scales, where each interaction strips away another layer of energy until only the neutrino remains, a stripped-down messenger carrying the signature of its birth trauma across the cosmos. But blazars aren't the only culprits. Some ultra-high-energy neutrinos may come from tidal disruption events, when a star strays too close to a black hole and gets shredded into a glowing debris disk. Others might originate in galaxy clusters, where colliding shockwaves accelerate particles like ocean waves hurling surfers toward the shore. There's even speculation about dark accelerators, sources we can't yet see, perhaps involving dark matter annihilation or other exotic physics. IceCube's design is as ingenious as the particles it seeks. Its sensors don't look for neutrinos directly, but for the muons or cascades produced when a neutrino against all odds collides with an atom in the ice. The detector's depth filters out cosmic ray noise, while the ice's clarity lets Cherenkov light travel hundreds of meters before being captured. When a neutrino interaction occurs, the entire array lights up like a subatomic alarm system, triangulating the particle's energy and direction with startling precision. The implications ripple far beyond astrophysics. Neutrinos, this energetic, challenge our understanding of particle interactions at energies unreachable in labs. Some models suggest they might reveal extra dimensions or other quantum anomalies. Others see them as probes of cosmic magnetic fields, their rare interactions subtly altered by forces we can't otherwise measure. Every trillion electron-volt neutrino is a Rosetta Stone decoding the language of cosmic violence. They remind us that for all our telescopes and satellites, some of the universe's starkest truths arrive not as light or radio waves, but as silent, nearly invisible particles whispering secrets from the darkest, most energetic corners of existence. Neutrinos are the ultimate cosmic chameleons, particles that can change identities mid-flight without warning. This bizarre behavior, called neutrino oscillation, upended decades of particle physics and earned its discoverers the Nobel Prize. Picture a runner starting a marathon as a sprinter, morphing into a long-distance specialist halfway through, then finishing as a hurdler. That's essentially what neutrinos do as they travel, switching between three distinct flavors: electron, muon, and tau. The phenomenon isn't just quirky. It revealed that neutrinos have mass, a discovery that forced scientists to rewrite the standard model of particle physics. The breakthrough came from an unexpected place: underground tanks filled with ultra-pure water. In the late 1990s, Japan's Super Kamiok detector noticed something odd. It was built to catch neutrinos produced by cosmic rays hitting Earth's atmosphere, expecting equal numbers coming straight down versus those arriving after traversing the planet. But the neutrinos that traveled farther, through 12,000 kilometers of rock, arrived with fewer muon neutrinos than predicted, the only explanation. These particles weren't disappearing, they were shape-shifting into tau neutrinos, which the detector couldn't see at the time. Here's the quantum weirdness at play. Neutrinos aren't strictly electron, muon, or tau types, but exist as quantum superpositions of all three. As they move, their quantum states evolve, causing the probability of measuring a particular flavor to oscillate. The heavier the neutrino's mass state, yes, they have tiny masses despite being nearly weightless, the faster this oscillation occurs. Solar neutrinos, born in the sun's core as electron neutrinos, often reach Earth as a different flavor entirely, a fact confirmed by the Sudbury Neutrino Observatory in Canada. What makes this discovery monumental isn't just the particle physics, it's the cosmic implications. Neutrino oscillations imply these particles must have mass, however slight. That mass, calculated to be less than 1/1,000,000th of an electron's, disrupts the pristine symmetry of the standard model. Suddenly, theories about how the universe formed had to account for these nearly massless particles subtly influencing cosmic evolution. Some cosmologists even speculate neutrino oscillations might explain why the universe contains more matter than antimatter, a puzzle known as Baryon asymmetry. The practical side is just as fascinating. Neutrino oscillation research birthed entirely new experimental techniques. Fermilab's NOVA experiment fires a beam of muon neutrinos through the Earth to Minnesota, watching how many transform into electron neutrinos over 800 kilometers. Japan's T2K experiment does something similar, sending particles from Tokai to Super Kamiok, and These efforts aren't just academic, they're refining our understanding of neutrino mass hierarchies, which could unlock why the universe favors matter over antimatter. Perhaps the most poetic aspect is how this quantum ballet connects us to stellar processes. When a supernova explodes, neutrinos oscillate as they flee the collapsing star, altering the flavor mix that reaches Earth. Future detectors might read these patterns like cosmic Morse code, revealing details about the star's composition and collapse mechanism. Even ice-bound observatories like IceCube rely on oscillation models to interpret their ultra-high-energy neutrino detections accurately. Neutrino oscillation reminds us that the universe thrives on transformation. Particles born in stellar furnaces don't arrive unchanged. They evolve, adapt, and surprise us. Every neutrino passing through you right now carries this quantum restlessness, a whisper from processes reshaping reality itself. And as detectors grow more sensitive, who knows what other secrets these shape-shifting messengers might reveal. Gamma-ray bursts are the universe's ultimate light, shows blinding flashes of energy so intense they briefly outshine entire galaxies. Lasting anywhere from milliseconds to a few minutes, these explosions unleash more energy than our Sun will produce in its entire 10 billion-year lifespan. What could possibly generate such mind-bending power? The answer lies in the catastrophic deaths of massive stars and the violent mergers of neutron stars, events so extreme they warp space-time itself while hurling jets of radiation across the cosmos at near light speed. The shortest bursts, lasting less than 2 seconds, typically come from collisions between neutron stars, city-sized remnants of dead stars so dense a single teaspoon would weigh 1 billion tons. When two of these ultra-dense objects spiral into each other, their merger creates a black hole almost instantly. The surrounding magnetic fields, twisted to unimaginable strengths during the collision, funnel leftover material into jets that blast outward like cosmic blowtorches. These jets generate gamma rays, the most energetic form of light, as they plow through surrounding gas, creating the burst we detect. But the fireworks don't stop there. The same event also shakes the fabric of space-time, producing gravitational waves detectable here on Earth, while spewing heavy elements like gold and platinum into the void. Longer gamma-ray bursts, lasting minutes or more, have an even more dramatic origin: the collapse of massive stars into black holes. As a star 20 to 30 times heavier than the Sun exhausts its nuclear fuel, its core implodes under gravity's crush. Instead of rebounding as a supernova, the collapse continues until a black hole forms. What happens next is like a cosmic reboot. Material falling toward the newborn black hole gets redirected into jets that drill through the dying star's outer layers. When these jets break free, they release a torrent of gamma rays visible across billions of light years. The afterglow, fading over days or weeks, often reveals the supernova that birthed it, confirming these bursts as the death cries of stellar giants. Detecting gamma-ray bursts requires instruments far beyond ordinary telescopes. Satellites like NASA, Swift, and Fermi constantly scan the skies for these flashes, their detectors tuned to the highest energy photons. When Swift spots a burst, it can swivel within seconds to capture the fading X-ray and ultraviolet afterglow, while ground-based observatories scramble to identify the host galaxy. Some bursts originate so far away we're seeing them as they were when the universe was a fraction of its current age, making them not just spectacular explosions, but time capsules from the early cosmos. What makes these events truly unsettling is their raw power. A gamma-ray burst within a few thousand light-years could strip Earth's ozone layer, triggering mass extinctions. Some scientists suspect a nearby burst may have contributed to the Ordovician extinction 450 million years ago. Thankfully, the nearest potential burst candidates are thousands of light-years away. Yet their very existence serves as a reminder: the universe isn't just vast and beautiful, it's also capable of violence on scales we can barely comprehend. The study of gamma-ray bursts has revolutionized astrophysics, linking phenomena once thought unrelated. A single burst might involve supernova, black holes, gravitational waves, and the creation of heavy metals, all in one cataclysmic package. They're cosmic Rosetta Stones, helping us decode how the universe's most energetic processes intertwine. And with every new detection, we're reminded that for all its apparent stillness, the cosmos is a place of unimaginable fury, where the birth screams of black holes and the collision of dead stars echo across the ages as the brightest flashes in the dark. Rising above and below the Milky Way like colossal hourglasses of pure energy, the Fermi bubbles stretch 25,000 light-years into space, twin towers of gamma rays so vast they dwarf our entire galaxy's visible disk. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these enigmatic structures glow with the energy of 100,000 supernova, yet their origin remains one of the most tantalizing puzzles in modern astrophysics. What cosmic force could have carved such perfect, symmetrical shapes into the fabric of our galactic neighborhood? The prime suspect sits at the very center of the Milky Way, Sagittarius A, our galaxy's supermassive black hole, currently dormant but possibly the architect of ancient violence. The bubble's scale defies comprehension. If you could see their gamma-ray glow with the naked eye, they would span half the night sky, each lobe stretching from the constellation Virgo to Grus. Their edges are razor-sharp, suggesting a single cataclysmic event rather than gradual buildup. Inside, the bubbles seethe with ultra-fast particles and magnetic fields, creating a gamma-ray fog that reveals itself only to specialized telescopes. What's startling isn't just their size, but their youth. Estimates suggest they formed between 2 and 4 million years ago, a blink in cosmic time when dinosaurs still roamed Earth. The leading theory points to a prehistoric feeding frenzy by Sagittarius A. Normally quiet, the black hole may have devoured a massive gas cloud or even a small galaxy, triggering twin jets of plasma that punched through the galactic halo. These jets, confined by the Milky Way's magnetic fields, could have inflated the bubbles like cosmic balloons, their shockwaves accelerating particles to near light speed. Supporting this idea are the bubbles matching X-ray and microwave signatures, telltale signs of ancient particle acceleration. Some models suggest the event released enough energy to briefly outshine all the stars in the Milky Way combined, a flash of cosmic violence hidden behind curtains of interstellar dust. But Sagittarius A isn't the only suspect. Alternative explanations include a burst of star formation so intense its supernova collectively blew a hole in the galactic atmosphere, or even dark matter annihilations in the galaxy's core. The bubble's perfect symmetry poses another riddle. How could any explosion remain so balanced across such distances? Some simulations suggest the Milky Way's magnetic fields acted like a mold, shaping the outflow into crisp geometric forms. Others propose the bubbles are actually overlapping shockwaves from multiple black hole eruptions over millions of years, their edges smoothed by time. The real breakthrough may come from studying the bubble's skin, the thin, bright rims where gamma-ray emission spikes. These edges could mark the shock fronts where the bubble material plows into intergalactic gas, like the bow wave of a ship sailing through space. Recent observations by the Hawk Observatory in Mexico revealed extremely high-energy gamma rays along these boundaries, hinting at particles being reaccelerated even today. It's as if the bubbles are still active, their engines faintly rumbling long after the initial explosion. What makes the Fermi bubbles more than a celestial curiosity is their connection to galaxy-scale ecology. Similar structures have been spotted in other galaxies, suggesting black hole outbursts might be universal regulators, preventing galaxies from growing too large by occasionally blasting away their gas reserves. The bubbles could also explain why the Milky Way's halo contains surprisingly few young stars. Their formation might have been quashed by the same shockwaves that carved these gamma-ray monoliths. Every new observation peels back another layer of mystery. In 2020, astronomers detected faint X-ray loops arcing away from the bubble's bases, possibly the remnants of the original jets that created them. Then there's the Fermi cocoon, a smaller gamma-ray structure nestled within the southern bubble, which might be a separate eruption or a ripple in the larger outburst. With plans to study the bubbles using next-generation neutrino detectors and upgraded gamma-ray telescopes, we're on the verge of decoding their full story, a story written in light and fury, hidden in plain sight above our heads every night. Stand beneath a truly dark sky, and you're gazing right through these invisible giants. They remind us that even our quiet galactic home has a violent past, and that the black hole slumbering at its heart might awaken again. The Fermi bubbles are more than relics, they're a warning and a wonder, proof that the universe writes its history not just in stars and planets, but in the echoes of explosions too immense to fathom. For decades, an eerie gamma-ray glow has haunted the heart of the Milky Way, a persistent whisper of light at exactly 511 kilo-electron volts, the fingerprint of electrons meeting their antimatter twins. This enigmatic signal, first spotted by gamma-ray satellites in the 1970s, reveals a staggering truth. Our galaxy's core produces enough positrons to annihilate with electrons at a rate of 10 to the power 43 times per second. That's 1 trillion tons of antimatter vanishing into pure energy every century, yet mysteriously concentrated within a few hundred light-years of Sagittarius A, the supermassive black hole anchoring our galaxy. Where this antimatter comes from remains one of astrophysics' most stubborn puzzles, with explanations ranging from dead stars to dark matter's ghostly decay. The 511 kilo-electron volt line is antimatter's death certificate, the precise energy released when an electron and positron collide and obliterate each other. Normally, such annihilations occur near environments like pulsars or supernova, where high-energy processes can spawn particle-antiparticle pairs, but the galactic center's signal defies expectations. It's too smooth, too widespread, and too bright for known astrophysical sources to explain. Maps from NASA Compton Gamma Ray Observatory and later the Integral satellite showed the glow isn't a point source, but a diffuse cloud enveloping the core, like a ghostly fog of annihilation. Even stranger, the signal exhibits asymmetry. It's stronger on one side of the galactic center than the other, as if some unseen hand were sprinkling antimatter unevenly across the void. Leading theories split into two camps, conventional and exotic. On the mundane side, astronomers posit that X-ray binaries, pairs where a neutron star or black hole strips material from a companion star, might be churning out positrons through particle cascades near their intense magnetic fields. Another candidate is radioactive isotopes like aluminum-26, forged in supernova and stellar winds, which decay into positron-emitting isotopes. Yet calculations suggest these sources fall short by orders of magnitude. They simply can't account for the sheer volume of antimatter annihilation observed. This discrepancy has thrust wilder possibilities into the spotlight. Some astrophysicists speculate that dark matter, the invisible glue holding galaxies together, might be decaying or colliding in ways that produce positrons. Certain hypothetical dark matter particles, like weakly interacting massive particles or WIMP, could annihilate with each other, yielding electron-positron pairs as byproducts. Others propose even stranger players, primordial black holes left over from the Big Bang, evaporating through quantum effects and radiating antimatter in their death throes. Then there's the truly radical idea that Sagittarius A itself might be manufacturing antimatter through processes we don't yet understand, perhaps involving its relativistic jets or the bizarre physics of its event horizon. The implications ripple far beyond astrophysics. If dark matter is indeed the culprit, the 511 kilo-electron volt signal could be our first tangible clue to its nature, a cosmic fingerprint waiting to be decoded. Future telescopes like the proposed E-astrogam mission aim to map the signal's distribution with unprecedented precision, searching for telltale clumps or patterns that might betray its origin. Meanwhile, laboratory experiments are hunting for dark matter particles that could decay into positrons, bridging the gap between cosmic mysteries and terrestrial physics. What makes this signal so mesmerizing is its duality. It's both a beacon and a riddle, a clear signpost pointing toward processes we can't yet see. Every photon at 511 kilo-electron-volts is a whisper from the universe's shadowy corners, where matter and antimatter dance their fatal tango. And until we crack its code, the galactic center's antimatter glow remains a testament to how much we still have left to discover in our own cosmic backyard. Detecting a photon with the energy of a flying mosquito sounds impossible until you realize that energy is packed into a single particle smaller than an atom. These are ultra-high-energy photons, cosmic light bullets carrying more than 100 tera-electron-volts, equivalent to the kinetic energy of a baseball moving at 60 miles per hour condensed into a speck of pure radiation. For comparison, that's about 10,000 times more energetic than particles accelerated in the Large Hadron Collider, arriving not from human-made machines but from nature's most violent engines scattered across the cosmos. The hunt for these extreme photons starts with a paradox: they shouldn't survive the journey to Earth. Space is filled with the cosmic microwave background, the afterglow of the Big Bang, which acts like a fog for high-energy light. When an ultra-high-energy photon collides with one of these low-energy background photons, they can annihilate each other, producing an electron and positron pair. Over intergalactic distances, this process should strip away most photons above 100 tera-electron-volts long before they reach us. Yet somehow they do arrive, challenging our understanding of how light travels through the universe's particle haze. Distinguishing these photons from ordinary cosmic rays is like trying to spot a single unique snowflake in a blizzard. Both types of particles trigger massive air showers when they hit the atmosphere, creating cascades of secondary particles that rain down over square miles. The key difference lies in the shower's structure. Cosmic rays, being protons or heavier atomic nuclei, interact strongly with air molecules, producing showers rich in muons, heavy, penetrating particles that reach the ground. Photon-induced showers, on the other hand, generate far fewer muons, since photons primarily create electron-positron pairs that quickly dissipate their energy. Detectors like the High-Altitude Water Cherenkov Observatory in Mexico exploit this difference, using grids of water tanks to capture the faint blue Cherenkov light from showers and analyzing their particle makeup to identify potential photons. But even with advanced instruments, false positives abound. A cosmic ray shower that happens to develop unusually late in the atmosphere might mimic a photon's signature, while a high-energy photon interacting early could be mistaken for a proton. To complicate matters further, some photons might convert into electron-positron pairs mid-journey, only to reconvert back into photons, effectively disguising their true nature. Scientists combat these uncertainties with statistical methods, collecting vast datasets to separate the true photon signals from the cosmic ray noise. The origins of these photons are as mysterious as their survival. Some likely come from supernova remnants where shockwaves accelerate particles to extreme energies. Others may be born in the relativistic jets of active galactic nuclei, where magnetic fields twist and snap, flinging photons outward like sparks from a cosmic forge. There's even speculation that some might be the byproducts of dark matter annihilation or other exotic processes we've yet to discover. Each detection is a puzzle piece, helping us map the universe's most efficient photon accelerators. What makes these photons more than just cosmic curiosities is their potential to unveil new physics. Their very existence hints at gaps in our understanding of photon propagation, or perhaps undiscovered mechanisms that replenish their energy during transit. Future observatories like the Cherenkov telescope array with its unprecedented sensitivity aim to catch these rarities in greater numbers, tracing them back to their sources with precision. Until then, every 100 tera electron-volt photon that streaks through our atmosphere carries with it a challenge, a dare to rethink what we know about light, energy, and the invisible barriers they overcome. Deep beneath the border of Switzerland and France, the Large Hadron Collider accelerates protons to energies that boggle the mind: 7 trillion electron volts per particle, making it humanity's most powerful machine. Yet out in the cosmos, nature operates accelerators that dwarf our greatest engineering feats, hurling particles with energies 100 million times stronger. The difference isn't just in scale, but in mechanism, where human colliders rely on precisely tuned electromagnetic fields in vacuum chambers. The universe uses shock waves from exploding stars, spinning black holes, and colliding galaxies to whip particles to unfathomable speeds. Take supernova remnants, the expanding debris fields from stellar explosions. As these shockwaves plow through interstellar gas at thousands of kilometers per second, they create turbulent magnetic fields that trap protons and electrons, bouncing them back and forth like ping-pong balls crossed with pinballs. Each pass gives the particles another kick, accelerating them over centuries to energies the LHC would need years to achieve. The Crab Nebula's pulsar alone, a rapidly spinning neutron star, generates electric fields so intense they accelerate electrons to 1,000 trillion electron volts, producing gamma rays detectable from Earth. Then there's the true heavyweights, active galactic nuclei. The jets screaming from supermassive black holes like those in Galaxy M87 act as particle accelerators stretching tens of thousands of light years. Magnetic fields coiled like springs along these jets sling charged particles outward, sometimes boosting them beyond 100 exa-electron volts energies, so high they make the oh my god particle look almost pedestrian. Unlike the LHC's controlled collisions, these processes are messy, chaotic, and unimaginably vast, turning entire galaxies into natural laboratories where the universe tests physics at energies we can scarcely replicate. The most humbling difference lies in duration. The LHC's acceleration happens in microseconds. Cosmic accelerators operate for millennia. A single particle might surf shockwaves across interstellar space for millions of years, gradually gaining energy until it rivals a speeding bullet, all from natural processes that require no power grid or superconducting magnets. And while the LHC produces maybe 1 billion collisions per second, a typical supernova remnant can simultaneously accelerate enough particles to populate every star in the Milky Way. Yet for all their might, cosmic accelerators share one crucial limitation with human-made ones: they can't violate the laws of physics. Both rely on the same fundamental principles: charged particles gaining energy from electromagnetic fields. The universe just has bigger tools, more space, and far more time. That's why studying cosmic rays isn't merely astronomy. It's particle physics at energies we'll never achieve on Earth, offering glimpses into how matter behaves under conditions no lab could recreate. Every high-energy cosmic particle we detect carries with it the signature of nature's ultimate accelerator, a reminder that for all our ingenuity, we're still newcomers in a universe that's been running the ultimate physics experiments for billions of years. Every living thing on Earth owes its existence to an invisible force, a relentless rain of high-energy particles that may have shaped life's very blueprint. Cosmic rays, those microscopic bullets from deep space, don't just pass through our bodies unnoticed. They leave behind traces of genetic chaos, occasionally snipping DNA strands or altering molecular structures in ways that ripple across generations. Some scientists now believe these particles played a crucial role in accelerating evolution itself, acting as nature's random mutation generators during life's most vulnerable stages. Consider Earth 4 billion years ago, a newborn planet with a thin atmosphere and no magnetic field to deflect incoming particles. cosmic rays would have bombarded the surface at rates hundreds of times higher than today, their ionizing radiation pummeling the primordial soup where life first stirred. While this sounds destructive, the chaos might have been essential. Laboratory experiments show that cosmic ray analogs can both break apart simple organic molecules and catalyze the formation of more complex ones, like amino acids, the building blocks of proteins. It's a paradoxical dance of creation and destruction, where high-energy particles could have simultaneously disrupted early life forms while providing the genetic variability needed for adaptation. The fossil record holds tantalizing clues. Periods of increased biodiversity often align with eras when Earth's magnetic field weakened, allowing more cosmic rays to penetrate. The Cambrian explosion, life's great diversification 500 million years ago, coincided with a geomagnetic reversal that left the planet temporarily unprotected. Similarly, spikes in mutation rates observed in ancient plant spores correlate with known cosmic ray events from supernova occurring within a few hundred light years. These aren't coincidences but potential signatures of particles rewriting life's code from the outside. Modern organisms still bear traces of this relationship. Certain extremophiles microbes thriving in radioactive environments use melanin not just for UV protection but as a quantum energy converter, possibly harvesting energy from cosmic ray byproducts. Some researchers even speculate that the human brain's development of protective mechanisms against radiation damage, like advanced DNA repair enzymes, might be an evolutionary echo of our ancestors' constant exposure to these particles. Yet the cosmic ray-life connection remains controversial. Opponents argue that while particles undoubtedly cause mutations, most are harmful or neutral, hardly the stuff of progressive evolution. They point to radiation's known dangers, from cancer risks to cellular damage, as evidence that cosmic rays more often disrupt than create. But proponents counter that in life's earliest stages, when organisms were far simpler, even destructive mutations could have opened new evolutionary pathways impossible through gradual changes alone. The most radical theories go further. Certain models suggest cosmic rays might have delivered not just mutations but the very ingredients for life. Hyper-energetic particles colliding with atmospheric molecules could have produced rare isotopes like carbon-14 or even complex organic compounds that rained down onto the young Earth. There's even speculation that chiral molecules, the handedness fundamental to life's chemistry, might have been influenced by polarized cosmic rays, selectively breaking down one molecular orientation over another. Today, this ancient interaction continues subtly in every cell. Your DNA withstands about 15 cosmic ray-induced lesions daily, most repaired instantly by molecular machinery fine-tuned over eons. Each time you catch a whiff of petrichor after a thunderstorm, you're smelling ozone created partly by cosmic ray ionization, a faint echo of the processes that may have sparked life's diversity. While we'll never know precisely how crucial these particles were to our origins, their fingerprints are everywhere, in our genes, our ecosystems, and the very air we breathe, reminding us that life didn't evolve in isolation, but under the invisible bombardment of the cosmos itself. Physics textbooks might need a rewrite. Nature keeps flinging particles at us that shouldn't exist according to our best theories. Over the past decade, detectors have captured cosmic rays with energies so extreme, they defy the very frameworks scientists use to explain the universe's most violent events. These aren't just outliers, they're direct challenges to our understanding of how matter, energy, and space itself behave at the highest conceivable scales. Take the so-called Amaterasu particle, detected in 2021 by the Telescope Array project in Utah. Clocking in at 240 exa-electron volts, it carried kinetic energy comparable to a brick dropped from waist height, packed into a single proton. What makes this detection so unsettling isn't just the particle's energy, but its trajectory. Unlike most ultra-high-energy cosmic rays, which point toward active galactic nuclei or other known accelerators, Amaterasu seem to come from nowhere, a void in the local supercluster devoid of any obvious cosmic powerhouse. If our models are correct, particles like this should have been stripped of their energy eons before reaching Earth by interactions with the cosmic microwave background. Yet here they are, laughing in the face of the GZK cutoff. Theorists are scrambling to explain these rule breakers. One radical idea suggests that ultra-high-energy particles might exploit quantum loopholes, briefly transforming into heavier, short-lived particles that interact less with the cosmic microwave background before reverting to protons mid-flight. Others propose that magnetic fields threading the voids between galaxies could act as hidden accelerators, giving particles second boosts that mask their true origins. The most mind-bending hypothesis that some cosmic rays aren't protons at all, but exotic ultra-heavy nuclei or even microscopic black holes evaporating via Hawking radiation, leaving behind particle signatures that look impossibly energetic. Each of these explanations comes with its own paradoxes. If magnetic reacceleration in voids is real, why don't we see more lower-energy particles from the same regions? If quantum shape-shifting occurs, why haven't lab experiments glimpsed hints of it? The lack of clear answers has revived interest in fringe theories once dismissed as too speculative ideas like Lorentz invariance violation, where the fabric of space-time behaves differently at energies so high that light's speed limit might not be absolute. Some models even suggest these particles could be evidence of higher dimensions, their true energy diluted as it leaks into our observable universe. What's at stake isn't just astrophysics, it's the foundation of modern particle theory. The Standard Model has no room for protons with energies hundreds of times beyond what the LHC can produce. Neither does general relativity fully account for how space-time mediates such extreme transfers of energy without breaking down. Every detection of an impossible particle forces us to confront the limits of our knowledge, hinting at a layer of reality where the rules might not just be different but unrecognizable. The hunt for answers is driving a new generation of experiments. China's Lhasa Observatory recently detected gamma rays with energies exceeding 1 peta-electron-volt, photons that, by conventional wisdom, shouldn't survive their journey through the cosmic microwave background. The upcoming Cherenkov telescope array aims to catch these rarities in greater numbers, while neutrino telescopes like IceCube Gen 2 will test whether extreme particles arrive alongside their ghostly counterparts. Even gravitational wave detectors are joining the effort, searching for ripples in space-time that might coincide with these cosmic anomalies. For now, each impossible particle remains both a revelation and a rebuke, proof that the universe operates machinery we haven't yet imagined, and a humbling reminder that for every law we've written about nature, there may be exceptions scribbled in margins we've yet to read. The more we study them, the clearer it becomes. These aren't flaws in the cosmic design, but signposts pointing toward physics beyond our current horizon. And somewhere out there, another particle is racing toward Earth, carrying energy that defies explanation, waiting to shatter another assumption we didn't realize we'd made. If you mapped every ultra-high-energy cosmic ray ever detected, expecting them to point back to their birthplaces like galactic breadcrumbs, you'd be in for a shock. Unlike light or gamma rays, which trace neat paths to distant quasars or supernova, cosmic rays arrive from all directions with baffling uniformity, a pattern scientists call isotropy. This isn't just odd, it's like throwing a handful of compass needles into the air and watching every one point randomly instead of north. The implications are profound. Either our understanding of cosmic magnetism is catastrophically wrong, or these particles are being scrambled on their way to Earth in ways we can't yet explain. The mystery deepens when you consider how cosmic rays should behave. Protons and atomic nuclei are electrically charged, which means they should curve along the Milky Way's tangled magnetic fields like marbles rolling through a maze. Over interstellar distances, these deflections should smear their arrival directions beyond recognition, wiping out any connection to their origins. Yet for the highest energy cosmic rays, those above 58 exa-electron volts, the physics flips. Their immense energy makes them nearly immune to magnetic bending, meaning their path should point straight back to their sources like cosmic laser beams. Except they don't. The Pierre Auger Observatory's painstaking sky maps reveal no clear hotspots, no clusters around active galaxies, just a sprinkling of particles that seem to hail from nowhere in particular. One explanation lies in our galactic neighborhood's magnetic fog. Recent simulations suggest the Milky Way's magnetic field might be far more chaotic than we thought, with local turbulences acting like funhouse mirrors that distort even ultra-high-energy particle trajectories. Picture a lighthouse beam passing through frosted glass. The light still comes through, but its original direction is obscured. Some theorists argue that nearby magnetic lenses could be redirecting cosmic rays from true sources we've already identified, like Centaurus A or M87, into seemingly random arrival angles. Others propose that these particles aren't coming from discrete sources at all, but from diffuse shockwaves permeating intergalactic space, where colliding galaxy clusters or dark matter filaments create sprawling particle acceleration zones without a single epicenter. Then there's the truly radical possibility that we're missing an entire class of cosmic accelerators. When the telescope array spotted a handful of ultra-high-energy events clustered in a patch of sky nicknamed the hotspot, astronomers scoured the region for likely sources. They found nothing obvious: no active galactic nuclei, no gamma-ray bursts, just a quiet stretch of cosmic backcountry. Similar voids appear in other surveys, hinting at invisible engines lurking in the darkness. Could these be decaying supermassive black holes we haven't detected? Primordial defects in space-time left over from the Big Bang? The frustrating truth is that without better magnetic field maps or higher resolution cosmic ray catalogs, we're left with more questions than answers. This isotropy isn't just an academic puzzle, it's a roadblock to solving cosmic rays' greatest mysteries. If we can't trace them home, we may never know for certain what launches these particles to such insane energies. Next-generation observatories like the upgraded Auger Prime aim to tackle this by measuring cosmic ray compositions mid-air, hoping that heavier nuclei's deflection patterns will reveal magnetic field secrets. Others are turning to neutrino and gamma-ray astronomy, seeking secondary messengers that might point back to the same sources. For now, the cosmic ray map remains a riddle written in vanishing ink, its scattered dots hiding more than they reveal. Every isotropic sky survey is a humbling reminder that for all our telescopes and supercomputers, the universe still holds cards close to its chest, and the particles screaming through our atmosphere might be carrying truths we're not yet equipped to decode. The next leap in cosmic ray science isn't happening on mountaintops or ice sheets. It's taking shape in blueprints for machines so advanced they'll catch particles we can barely imagine studying today. Leading this charge are two revolutionary projects, the Cherenkov Telescope Array and the Probe of Extreme Multi-Messenger Astrophysics. These aren't incremental upgrades, they're complete reinventions of how we observe the universe's most energetic particles, designed to peer deeper into cosmic mysteries than ever before. Imagine a telescope that doesn't just look up but all around, an observatory with eyes on the entire sky at once. That's POMA radical approach. This proposed space mission consists of two satellites flying in formation, armed with ultraviolet cameras to catch the faint fluorescence trails left by ultra-high-energy cosmic rays striking Earth's atmosphere. Unlike ground arrays limited by weather and geography, POMA would orbit above the clouds, watching particle showers develop across continents with unobstructed views. Its design tackles one of cosmic ray astronomy's biggest hurdles, the rarity of extreme events. By covering the entire planet's atmosphere simultaneously, POMA could detect dozens of ultra-high energy cosmic rays annually compared to the handful caught by current detectors over decades. Meanwhile, back on Earth, the Cherenkov telescope array is redefining gamma-ray astronomy. Spread across sites in Chile and the Canary Islands, this next-generation observatory will combine over 100 telescopes of various sizes into a single coordinated network. Where current gamma-ray detectors struggle with fuzzy images and limited energy ranges, CTA's multi-scale approach achieves razor-sharp resolution across an unprecedented energy spectrum from 20 giga-electron-volts to 300 tera-electron-volts. The secret lies in its tiered design. Large telescopes catch the faint, high-energy showers, while smaller ones track bright, lower-energy events, creating a seamless window into particle physics from both ends of the energy scale. What sets these projects apart isn't just their scale, it's their embrace of multi-messenger astronomy. POMA will hunt not just cosmic rays, but their neutrino and gamma-ray counterparts from the same cosmic sources, creating trifecta observations that could finally pinpoint cosmic accelerators definitively. CTA, paired with gravitational wave detectors and neutrino observatories, aims to catch the full aftermath of neutron star collisions or black hole eruptions across every available signal type. This coordinated approach transforms single particle detections into rich cosmic narratives, where each messenger adds another layer to the story. The technological leaps enabling these projects border on science fiction. POMA fluorescence detectors use space-qualified photomultipliers so sensitive they can spot a particle shower's UV glow from 600 kilometers away, equivalent to detecting a single light bulb in a city viewed from orbit. CTA's cameras employ silicon photomultipliers that operate at nanosecond speeds, capturing particle showers in freeze-frame detail impossible with current technology. Both systems feed data into AI-powered analysis pipelines capable of reconstructing cosmic ray properties in real time, a far cry from the months-long analyses of past decades. Perhaps most exciting is what these detectors might reveal. CTA could finally solve long-standing mysteries like the origin of galactic cosmic rays by mapping the precise acceleration zones within supernova remnants. POMA whole sky coverage might uncover whether ultra-high-energy cosmic rays cluster around supermassive black holes in predictable patterns, or if we've been missing some even more exotic source all along. Together, they'll test theories about cosmic ray propagation through intergalactic space with unprecedented precision, potentially revealing hidden properties of the universe's magnetic web. The data deluge from these projects will dwarf anything in astrophysics history. POMA alone could generate petabytes annually, enough to fill a library of hard drives stretching from Earth to the International Space Station. Managing this flood requires computing architectures borrowed from particle physics and machine learning, turning what was once a data-starved field into a powerhouse of big data astronomy. The discoveries won't come from individual eureka moments, but from mining patterns across millions of events, a task perfectly suited for the AI era. These detectors represent more than just new tools, they're gateways to an unexplored energy frontier. As construction begins on CTA's first telescopes and POMA moves through mission design reviews, we're witnessing the dawn of a new age in cosmic ray science. The particles that have puzzled us for over a century may finally give up their secrets, not because we got lucky with a few rare detections, but because we've built machines that can force the universe to answer our questions on command. The era of cosmic ray astronomy as a passive observational science is ending. Welcome to the age where we don't just watch the particle storm, but dissect it atom by atom. From blockbuster films to sci-fi novels, cosmic rays have fueled countless fictional plots, though Hollywood often takes liberties with the truth. Marvel's Fantastic Four gives cosmic radiation near magical powers, transforming ordinary astronauts into superhumans with stretchy bodies or fiery fists. In reality, an unprotected human exposed to such intense particle bombardment wouldn't gain abilities. They'd face severe radiation sickness or worse. Yet this trope persists, from the Incredible Hulk's gamma-ray origins to Spider-Man's genetically altered spider, blending real physics with comic book fantasy. Television isn't much better. The Big Bang Theory once joked about cosmic rays causing spontaneous human combustion, while the X-Files tied them to alien abductions. Even Doctor Who depicted them as a sentient force rewriting DNA, a dramatic leap from their true nature as mindless high-speed particles. These portrayals aren't just harmless fun, they shape public perception, leading to widespread myths. Surveys show nearly 1 in 5 people believe cosmic rays could grant superpowers, while others fear they're a stealth health hazard worse than nuclear waste. Literature offers slightly more nuance. Kurt Vonnegut's Cat's Cradle imagined Ice 9, a cosmic ray-mutated substance freezing Earth's oceans, a metaphor for unintended consequences, not real science. Michael Crichton's The Andromeda Strain took a harder approach, using cosmic rays as a plausible catalyst for extraterrestrial microbes. Yet even these grounded stories exaggerate cosmic rays' mutational potency. In truth, while they do cause genetic damage, the mutations are random and far more likely to harm cells than create advanced organisms. The gaming world takes creative license to extremes. Fallout series mutants owe their existence to FEV, a virus enhanced by cosmic radiation, while Mass Effect depicts them as a rare energy source. These fictional twists reflect a deeper cultural theme. Cosmic rays as a stand-in for the unknown, a force that can explain anything strange or inexplicable. It's a storytelling shortcut, but one that obscures their true role as natural, if extraordinary, astrophysical phenomena. Some media do get it right. Cosmos, both Sagan's original and Tyson's reboot, accurately depicts cosmic rays as celestial messengers. The documentary Particle Fever showcases real scientists hunting for cosmic ray secrets at CERN. Even The Martian nods to their real-world risk, with astronauts shielding themselves during solar storms. These exceptions prove that facts can be as compelling as fiction, no superpowers required. The irony: cosmic rays are capable of things stranger than fiction. They've been caught flipping bits in computer code, triggering auroras, and possibly influencing cloud formation. No screenwriter needed to embellish that. The next time you see them invoked as a plot device, remember, the truth about these particles, their origins, their journeys, their impact is dramatic enough without the Hollywood hype. For all we've uncovered about cosmic rays, the most thrilling chapters of their story remain blank pages. Even after a century of study, these particles guard their deepest secrets fiercely: how they reach energies that defy physics, where exactly they come from, and what they might reveal about the universe's most hidden corners. Take the enigma of their acceleration mechanisms. We know supernova and black holes play a role, but the math rarely adds up. How can a stellar explosion's shockwave, powerful as it is, propel particles to energies 100 million times beyond what our most advanced colliders achieve? Some theorists speculate we're missing a critical piece, perhaps magnetic reconnection, events far more violent than we've observed, or exotic plasma dynamics in the turbulent wakes of galaxy collisions. Others wonder if dark matter annihilation or even primordial cosmic strings, defects in space-time from the Big Bang, might be lurking in the data, invisible to our telescopes but leaving fingerprints in the particles they hurl our way. Then there's the puzzle of composition. Why do some ultra-high-energy cosmic rays arrive as lone protons, while others seem to be heavy nuclei like iron? If they're forged in the same cataclysms, shouldn't their ingredients be more consistent? The discrepancies suggest wildly different birthplaces. Perhaps protons come from the relativistic jets of active galaxies, while heavier nuclei are spat out by neutron star mergers. But confirming this would require tracing their paths back to sources with pinpoint accuracy, a near impossible task when galactic magnetic fields bend their trajectories like funhouse mirrors. Future observatories like the Cherenkov telescope array aim to crack this by correlating cosmic rays with neutrino and gamma-ray signals, triangulating their origins across multiple messengers. The biggest head-scratcher of all, those inexplicable particles that crash through theoretical speed limits. The GZK cutoff, a cosmic barrier that should prevent ultra-high-energy particles from traveling more than 100 million light-years, keeps getting violated by detections like the Oh My God and Amaterasu particles. Either these outliers originate shockingly close to us in cosmic terms, implying unseen accelerators in our galactic backyard, or something's fundamentally wrong with our understanding of how particles lose energy across intergalactic space. A handful of radicals even propose these anomalies hint at new physics, extra dimensions altering energy dissipation, or quantum gravity effects emerging at energies so high they warp the rules of relativity itself. What's next in this cosmic detective story? Imagine discovering that high-energy neutrinos, those ghostly particles Ice Cube detects, always arrive seconds before their cosmic ray counterparts from the same event. That timing could reveal how particles get boosted in bursts, like cosmic whiplash from black hole jets, or picture mapping the Milky Way's magnetic fields in 3D using machine learning, finally untangling the paths of wayward particles to reveal their true sources. There's even a chance we'll find cosmic rays linked to phenomena we can't yet explain, like fast radio bursts or those bizarre cosmic radio circles that appeared in recent sky surveys. The most exciting possibilities lie beyond current theory. What if some cosmic rays aren't particles at all, but microscopic black holes evaporating via Hawking radiation, leaving behind explosive signatures as they vanish? Could they be evidence of cosmic defects, topological kinks in space-time predicted by string theory? Every unexplained detection is a clue, a breadcrumb leading toward revelations that might rewrite textbooks. With next-generation detectors coming online, from space-based fluorescence telescopes to underground arrays sniffing out rare interactions, we're on the verge of turning these mysteries into breakthroughs. One day, we might look back at this era the way we view early chemists puzzling over alchemy, standing at the threshold of a deeper truth, unaware of the revolutions ahead. The universe's most energetic particles aren't just messengers, they're invitations to explore frontiers we've barely imagined. And the next time a cosmic ray streaks through you, remember, it might carry the answer to a question we haven't even thought to ask yet. From the ghostly whispers of neutrinos to the universe-shattering fury of gamma-ray bursts, our journey through cosmic rays has revealed just how much energy crackles through the void, often in ways that defy logic. Think about this: every second, invisible particles older than Earth itself slice through you, carrying the echoes of supernova and black hole feasts. Some pack the punch of a fastball in a speck smaller than an atom. Others arrive from voids so empty we can't even guess their origins. And despite decades of research, the simplest questions still taunt us. How does nature accelerate particles to energies 100 million times beyond our best colliders? Why do some cosmic rays ignore the universe's speed limits? The deeper we dig, the stranger it gets. Take those ultra-high energy particles that shouldn't reach us, the ones theorists swear must be stopped by the cosmic microwave background. Their very existence hints at gaps in physics we've yet to imagine. Or consider how cosmic rays might be architects of life itself, seeding mutations in DNA while sparking chemical reactions in primordial soups. Even now, they're rewriting bits in your phone's memory and sculpting storms in Earth's atmosphere. Yet for all we've uncovered, the cosmos guards its best secrets. What launches particles with the energy of a lightning bolt in a single proton? Are there dark accelerators lurking beyond our telescope sight? Every detection is a clue, but the full picture remains just out of reach, a puzzle with half the pieces still missing. That's the beauty of cosmic rays. They're not just answers, but invitations to ask bigger questions. So stay curious. The next breakthrough might come from a detector buried in Antarctic ice, a satellite watching Earth's atmosphere, or even your own backyard experiment. The universe is brimming with mysteries, and cosmic rays are just one thread in a tapestry we're only beginning to unravel. If you're as captivated as we are by these invisible messengers, hit subscribe, because the universe has plenty more secrets to share, and we're just getting started.